At this point in the course, you may be wondering how causal graphs look like. Okay, this is the moment that you have been waiting for. Meet your first causal diagram. This is a causal diagram with three variables or nodes, L, A, and Y. These variables are connected by arrows, which are also known as directed edges. This is the causal graph that we would draw if we knew that L has an effect on A and A has an effect on Y, and also L has a direct effect on Y that is not mediated through A. If we knew that some of these causal effects were not present, we would omit the corresponding arrow. And because the arrows indicate the direction of causality, we refer to this graph as a directed graph. So L causes A, but A doesn't cause L. This graph has another important property. It is acyclic. That is, there are no cycles. Meaning that if you start at one variable and follow the direction of the arrows, you will never get back to the same variable. L causes A and A causes Y, but then Y doesn't cause L. If you think of time as going from left to right on the graph, then that the graph is acyclic just means that the past affects the future, but the future doesn't affect the past. And because these graphs are directed and they're acyclic, we refer to them as DAGs, directed acyclic graphs. Sometimes we will say causal graphs, sometimes we will say causal DAGs. We mean exactly the same thing. And we draw DAGs by using our expert knowledge about the problem under study. If our expert knowledge is insufficient for us to exclude any possible effect, then we will draw all the arrows like we did in the previous graph, and we say that the DAG is complete. On the other hand, if our expert knowledge allows us to exclude some causal effects, then we will omit some of the arrows in the DAG. That's how we represent our knowledge, in the form of missing arrows. And DAGs are used for many things, not only for causal inference. Here we are going to be dealing with causal DAGs. A DAG is a causal DAG if, when two variables on the graph share a cause, that cause is also represented on the graph. This is known as the causal Markov condition. Let's see a couple of examples. Suppose that we are interested in the effect of aspirin A on the risk of a stroke Y. And let's say that we have conducted an experiment in which 10,000 individuals were randomly assigned to receiving aspirin and 10,000 individuals were randomly assigned to not receiving aspirin. Now, for each person, we flip a coin. Heads, you get aspirin. Tails, you don't get aspirin. So A represents assignment to aspirin. The question is, do we need to add any more variables other than A and Y to the graph to make it a causal graph? For example, you may be wondering about all these variables that are causes of Y, all the causes of a stroke that we know, like high blood pressure or coronary heart disease, diet, genes, and many, many others. Shouldn't we add these variables to the graph? Well, let me ask you something. Do any of these variables affect assignment to aspirin? No, of course not. This is a randomized trial. The only reason why some people got aspirin is because we flip a coin and that was heads, not because they had heart disease or because they had a high blood pressure. Therefore, all those causes of Y cannot possibly be causes of A. They are not common causes of Y and A, and therefore we don't need to include them in the graph. The simple graph that has A arrow Y is a causal DAG, even if it does not include all those other causes of Y. Now consider a different situation. Rather than having conducted a randomized trial, we did something very different. We selected a large number of individuals and classified them into two groups according to the information in their electronic medical records. In one group, we put everybody who started treatment with aspirin, and in the other group, everybody who didn't start treatment with aspirin. So now A in our graph represents aspirin use. Again, the question is, do we need to add any variables other than A and Y to our graph to make it causal? Okay, let's think about some of these causes of stroke, Y, that we discussed before. Take coronary heart disease. Should we have an arrow from coronary heart disease into A? Yes, because people who have coronary heart disease are more likely to start treatment with aspirin in the real world. Therefore, coronary heart disease is a common cause of A and Y, and it should be included in the graph. So, a causal graph for aspirin and stroke that does not include coronary heart disease is not a causal DAG when we are not randomizing treatment, and therefore that graph without coronary heart disease cannot be used to guide causal inference, as we will discuss in future segments. We have now seen our first causal graphs. In the next segment, we will start to explore the reasons why we like them so much.